Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. In this session, we are going to study the bending stress problems in beams. So, the course outcome related to this topic is that apply the knowledge of theories of failure, shear force, and bending moment relations for analyzing the flexural stresses, shear stress distributions, and failure of beam sections. So the Bloom's taxonomy for this session is the apply. Now let us start a problem of here. The problem is that a steel plate of width 120 millimeters and of thickness 20 millimeters is bent into a circular arc of radius 10 meters. Determine the maximum stress induced and the bending moment which will produce the maximum stress, and the modulus of elasticity for this material here it is 2 into 10 power 5 Newton per square millimeter. Now here the given data is here the width, that is the width of the plate 120 millimeters and the thickness is 20 millimeters, and we have to find out the maximum stress induced and bending moment. We know the relation that sigma by y equal to m by I equal to E by R. Here the modulus of elasticity we can know, and also radius of curvature. The radius of curvature here it is mentioned as 10 meters. Now we want to find out the maximum stress sigma by y equal to E by R. How to start? Here we know the moment of inertia, that is Bt cube by 12. Therefore, here the steel plate having the width and thickness. The thickness is the T and the width B. So about x-axis we want, that is the moment of inertia. For that about neutral axis Na parallel to the x-axis, that is Bt cube by 12. Where B is the width of the plate, that is 120 millimeters, T is the thickness 20 millimeters by 12, Bt cube by 12, that is 80 into 10 power 4 millimeter per 4. And the data given here it is radius of the curvature. The radius of the curvature here it is 10 meters. Convert into millimeters. Why it is? Because the moment of inertia is in millimeters. Convert the radius of curvature into millimeters. 1 meter equal to 1000 millimeters. That is 10 into 10 cube, that is 10,000 millimeters. Where Young's modulus of elasticity equal to 2 into 10 power 5, that is Newton per square millimeter. We know the relation between, that is sigma by y equal to E by R, that is sigma equal to E by R into y. Now what is the y maximum here? If it is y maximum, then sigma becomes sigma maximum. So what is the y maximum? The thickness of the plate, the neutral axis. What is the y maximum? When t by 2, when y equal to t by 2, y becomes y maximum. So that is thickness is 20 by 2, that is 10 millimeters. So sigma maximum equal to E by R into y maximum. So substitute over here the values of modulus of elasticity and radius of curvature and the y maximum value of y, that is 2 into 10 power 5 in the place of r value, that is 10 into 10 cube, and y maximum is 10. All are in homogeneous, that is in millimeters. E is in Newton per square millimeter, r is in millimeters, and y maximum is also in millimeters. Then the value, the sigma maximum equal to this 2 into 10 power 5 get cancelled, 10 power 4, that is 200 Newton per square millimeter. That is the sigma maximum. We know the simple bending equation, that is sigma by y equal to m by I equal to E by R. We know E and R ratio, we want bending moment. That bending moment comes m equal to E by R into y. What is it? E by R? E by R into I. What is the here? It is E equal to modulus of elasticity, that is 2 into 10 power 5. R radius of curvature 10 meters, convert into millimeters, 10,000 millimeters, and I What is the I value? Moment of inertia. Which moment of inertia? Here it is, the area moment of inertia. That one as calculated, that is BTQ by 12. BTQ by 12, that is 8 into 10 power 4. Substitute over here, then the value of bending moment is obtained. The value of bending moment is 16 to 10 power 5 Newton millimeter. That is 1.6 kilonewton meter. 1.6 kilo. This is 16 into 10 power 5 Newton millimeter. This is 1.6 into 10 cube into 10 cube. This is kilo newtons and it is 10 cube. Meter, millimeters converted into meters. 10 cube millimeters, 1000 millimeter equal to 1 meter. That's why it becomes 1.6 kilo Newton meter. This is the bending moment value. Now here it is considered in this problem. It is a plate having a width and a thickness, and the moment of inertia we found out from the formula of BTQ by 12 because it is parallel to, when to use TBQ by 12, it is the parallel to y-axis. Then is the B is the width, T is the thickness. Then if it in that case the moment of inertia about y, that is TBQ by 12. So in that manner we have to solve the problem. We found out in this the objectives are, the objectives, objective 1 is maximum bending stress and objective 2 is bending moment, and the input parameters are width of the plate, thickness of the plate, and two more parameters are modulus of elasticity and radius of curvature. These are the four parameters. We used here simple bending equation, that is sigma by y equal to m by I equal to E by R. This equation is known as pure bending equation or simple bending equation. Coming to the next problem, here it is the problem related to the hollow component. So it is hollow iron pipe. So here calculate the maximum stress induced in a cast iron pipe of external diameter, that is 40 millimeters, and internal diameter is 20 millimeters, and of length 4 meters. The length of the pipe is 4 meters. The outer diameter of the pipe, that is external diameter, is 40 millimeters, and internal diameter is 20 millimeters. When the pipe is supported, it is supported means it is like acting as simply supported. Both the ends it is supported. Now, and it carries, and it at its ends, supported at its ends, and carries a point load of 80 newtons at its center. Here it carries a point load 80 newtons at its center. So what to be found? Here the objective is that maximum stress induced because of this point load on the pipe, which is having the dimensions of 40 millimeter external diameter and internal diameter is 20 millimeters, and the length of the pipe is 4 meters. Now here it is 18 newtons at the center. When it is the point load, what the stresses are being induced, the maximum stress induced in this pipeline. Now the maximum stress comes, again we know the relation, that is pure bending equation, sigma by y equal to m by I equal to E by R. M by I equal to E by R. By using this relation, we can find out the unknown. What is that unknown? Here sigma maximum. Now, which relation we have to, shall we use? That is sigma by y equal to m by I or sigma by y equal to E by R. So based on the data here, the radius of curvature is not mentioned and the modulus of elasticity of the material also not mentioned. So we have to use the relation, that is sigma by y equal to m over I. By using this relation, we can find out the sigma maximum. So we have to know the maximum bending moment and moment of inertia of the hollow cylinder. The moment of inertia of the hollow cylinder can be calculated based on the dimensions given here, and bending moment m can be calculated by considering here it is a simply supported beam having a point load at the midpoint. Then what is the maximum bending moment? Then y becomes y equal to d by 2. There is capital D by 2, that is 40 by 220 millimeters. So the sigma maximum can be calculated. Let us begin. We have to find out maximum bending moment for simply supported beam. Here the maximum bending moment for a simply supported beam is subjected to a point load. For this condition, for a length L, so for the maximum bending moment for this case study for simply supported beam, because here it is mentioned that the pipeline is supported at its ends and the load 18 newtons is acted at the midpoint of the pipeline. The overall length of the pipeline is 4 meters. So WL by 4. What is the W here? 18 newtons. L converted into, here it is 4 meters converted into millimeters, that is 4000 millimeters. 80 into 4000, 4. So thus we can calculate 18 to 10 power 4 Newton millimeter. This is the bending moment, maximum bending moment, or the bending moment here it is 8 into 10 power 4 Newton millimeters. And the moment of inertia of a hollow pipe, the formula for it is, for moment of inertia is I equal to pi by 64 into capital D power 4 minus small d power 4. Pi by 64, capital D is 40 millimeters, small d is in 20 millimeters. After substituting the value observed here, it is 117,809.7 millimeter per 4. M we know, I we know. Our equation is sigma by y equal to m by I. M is calculated and A. What is the y? Y maximum. This is y equal to y, that is y maximum equal to capital D by 2. That is 40 by 2. That is 20 millimeters. So y we know, y calculated m and I. Then the sigma maximum can be calculated of substituting in this equation. That the equation of here it is used as pure bending equation. That is sigma by y maximum, sigma by y. Then that is sigma, what is the sigma value comes, that is output, m value 8 into 10 power 4, I that is 117,809.7 into y maximum, that is capital D by 2, that is outer diameter by 2, that is 20 millimeters. After substituting in this equation, the sigma maximum value is observed as 13.58 Newton per square millimeter. Newton per square millimeter. Why here it is Newton per square millimeter? This is m is in Newton millimeters, y is in millimeters. M here it is in Newton millimeter. The units of y it is in millimeter. I mass moment, area moment of inertia, it is in millimeter per 4. So all this geometrical, yes, that is called here it is. We followed a dimensional unity, homogeneity. So that's why sigma maximum comes in Newton per. That is Newton per millimeter square is observed. That is 13 point. The observed sigma maximum here it is 13.58 Newton per square millimeter. So here the novelty of this problem is that one is, there are two things in relation to the before problem and this problem. In before problem it is a solid plate, here it is a hollow pipe. The moment of inertia, area moment of inertia is different. Here it is a hollow pipe considered as a hollow cylinder and supported at its ends. For a 4 meter length of pipe is supported at its ends, and also it is subjected to a point load at its midpoint. So one is bending moment calculation, another one is area moment of inertia. These two are calculated. From that we can observe that sigma maximum stress is calculated. The maximum stress observed in this formula, in this problem here it is 13.58 Newton per square millimeters. Coming to here, yes, very important concept here, it is section modulus. What is the significance of section modulus? So the section modulus is the ratio of I and y maximum. So in mathematically, this is I by y, where I is the area moment of inertia and y becomes y maximum, that is the distance of the outermost layer from the neutral axis. Now here, this formula, the section modulus, came from the simple bending equation or theory of bending equation, that is sigma by y equal to m by I equal to E by R. If we compare the relation between these two, sigma by y equal to m by I, from that sigma equal to m by I times y, or we can make it m equal to sigma by y into I. So sigma times I by y. If m becomes m maximum, m becomes m max when y becomes y maximum. So that is m equal to sigma by sigma times I by y max, I by y. M maximum bending moment equal to sigma times I by y maximum. So when I by y maximum is nothing but that is Z maximum, that is called section modulus. That's so M maximum, a maximum of M equal to sigma times Z. So another formula for bending moment equal is the maximum stress times the section modulus, or section modulus times the maximum stress sigma. So here, where I is the moment of inertia about neutral axis, it is not about some axis. Then here it is moment of inertia about neutral axis of individual geometry. Now, one more thing is that there is another theorem that is called Parallaxis Theorem. This Parallaxis Theorem says that Ixx equal to Ig plus Ay bar square. Suppose about some xx axis, then Igx plus A into y bar square. So this Parallaxis Theorem, according to Parallaxis Theorem, this is. But here this Ig is the, about this Ig is the moment of inertia about neutral axis or centroidal axis. The centroidal axis means centroidal or IGX. Yes, neutral axis parallel to the centroidal axis, where A is the area of cross section of geometry and bar Y is the centroid from the reference axis. So this is the parallel axis theorem. But whereas higher I here it is mentioned is moment of inertia about neutral axis. So it is denoted by Z letter. So what is the unit? The unit for section modulus, that is, can be defined as here I by y max, where I is in millimeter per 4 and y is in millimeters. So for section modulus it is 3 times. So Z equal to I by y max. The unit for section modulus here it is mm cube. Unit for section modulus is mm cube or meter cube. So in that manner we can calculate I by y max, that is Z. So when sigma will be maximum, y becomes maximum. Very important is that here in this formula m equal to sigma maximum times Z, it is calculated step by step mentioned. M by I equal to sigma max by y max, m equal to sigma max I by y max, I by y maximum equal to Z, then m equal to sigma maximum times Z. Sigma maximum times Z. What is the physical significance of the Z? Yeah, where Z is the section modulus, but here M is the maximum bending moment or moment of resistance offered by the section the moment of resistance offered by the section. In this equation, maximum bending moment means the maximum resistance offered by the section. So if the moment of resistance of the section is maximum when the section modulus is maximum. So moment of resistance is maximum means what? It represents, that means more resistance is there, that means it's having more strength. That's why here it is section modulus represents the strength of the section. Section modulus represents the strength of the section. It's very important, here it is. So based on the section modulus of the section, one can find out, or one can recognize, one can give value the strength of the section. So at various sections, suppose there may be a rectangle and a square, triangular cross section, I section of the beams, C section, yes, various sections. How can you know which section is the best one? It depends upon the section modulus value. One of the parameters is the section modulus of the section. Now we are going to study the various section modulus of the various geometries or various sections. Here it is the rectangular section. The depth is the d and the breadth is the beam. So I by y maximum, what is the I value? This I is the moment of inertia about neutral axis. About neutral axis parallel to x-axis, that is neutral axis b dq by 12. I equal to b dq by 12. And y maximum, then what is the y maximum? Y stand for y maximum means the distance from neutral axis to outside the layer, topmost layer. The topmost layer is this position, that is the d by 2. So y max equal to d by 2, I equal to b dq by 12. Substitute here I by y maximum. I by y max b dq by 12 times d by 2. D get cancelled. B d square by 6. So the section modulus for rectangular section is, mathematically it is a bd square by 6. Unit for section modulus is millimeter cube. Unit for I, that is area moment of inertia, is mm for 4. Next, another section, it is a hollow rectangular section. This is a hollow section. The outside width is the larger width is the b, inner width is small b, and capital D outer side depth, and inner depth is small d. Now what is I value? The I value is about neutral axis, that is b, capital letters capital B, capital dq by 12 minus small letters b dq by 12. If we make it 1 by 12 is the common, capital B dq minus small b dq. Now what is the y maximum? What is the meaning of y max? Distance from neutral axis to topmost layer, that is d by 2. So substitute here z equal to I by y max. What is the I value? B dq by 12, b dq minus small b dq by 12 by d by 2. After simplification, the section modulus is calculated in terms of breadth and depth, that is capital B, capital letters b dq minus small b dq by 6 times d, depth, capital D. So when d increases, the z value decreases. When d decreases, it depends upon the value of section modulus is dependent on the b and d, depth and breadth of the section. So and one more, it is inversely proportional to capital D. If capital D increases, okay, in that manner, okay, this is the effect on depth affects the section modulus of the geometry. Another section, here it is circular cross section. For a circular cross section, if it is the diameter is the d is the diameter. Unit for diameter is millimeters. So for a circular cross section, the area moment of inertia is pi d power 4 by 64. What is the Y max? The Y maximum equal to d by 2. Substitute in this formula, that is in this relation, Z equal to I by Y max, where I is pi d power 4 by 64 and Y maximum is d by 2. Then it becomes 32 and d pi d cube by 32. After simplification, the section modulus is observed for a circular cross section is pi d cube by 32. What is the unit here? Section modulus. It is millimeter, cubic millimeter. And whereas unit for area moment of inertia, I, unit for I is millimeter per 4. Unit for Y maximum is millimeters. So I by Y max, millimeter per 4 by millimeter, that is millimeter cube. The next section, we can observe it is for a hollow circular section. Okay, the section modulus for the hollow circular section. For hollow circular section, I equal to, again, the section modulus relation for, what is the section modulus for hollow, or in principle section modulus formula is I by Y maximum. What is the I for? I for this is a hollow circular section, that is pi times capital D power 4 minus small d power 4 by 64 and Y maximum equal to d by 2. Substitute this I and Y in this, Z equal to I by Y max. I is pi by 64 times capital D power 4 minus small d power 4 and it is d by 2. Then again the Z value becomes pi times capital D power 4 minus small d power 4 by 32 times capital D, where capital D is outer diameter and the small d here it is inner diameter. Okay, and maximum distance from Y maximum is distance from Y max is the distance from neutral axis to topmost layer. This is Y max. That Y maximum equal to, what is the topmost layer? Capital D by 2. Okay, and if you substitute this Y maximum and moment of inertia values, then Z equal to comes I by Y max, where I is the area moment of inertia, Y max equal to capital D by 2. Thus, it is observed as section modulus value is I by 32D into capital D power 4 minus small d power 4. This is the moment of inertia, or the moment of inertia value is pi by 64 times capital D power 4 minus small d power 4. But the section modulus, again, it is pi by 32 times d capital D power 4 minus small d power 4. Again, what are the units for this section modulus? The units for section modulus is millimeter cube. Units for, again, moment of inertia is millimeter per 4. So these are the section modulus for various shapes. We can see here it is. This is for rectangular section B and D. We have already studied the IXX, that is the BD cube by 12 about neutral axis. That is, but here the section is different about XX axis. Here it is. The section modulus for this is the BD square by 3. Again for this section, based on BD cube by 12 about neutral axis. Here these are the passing through neutral axis, that is BD cube minus BD cube by 12. This is for Z section. This is for I section. dissection is considered here. And what about another section, that is C section? These are the various values for various sections, section modulus and second moment of area, that is known as moment of inertia. Okay, in this class we have covered and what are the section modulus and also solved problems on pure bending, theory of pure bending. That is, theory of pure bending is sigma by y equal to m by I equal to e by r equation. We solved problems and we learned what is section modulus, how to calculate section modulus, and what is the physical significance of section modulus. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.